Okay, so today we're going to be looking at how vertical asymptotes affect our limit problems. And you're going to notice that the answers for our limit problems have something to do with infinity. Again, vertical asymptotes, the answers have to do with infinity. Okay, so infinity is a concept that we use in mathematics when our values go increase without bounds. So it's not an actual number, and it's not a particular value. That is why you may have seen in interval notation, we don't include it. We use a parentheses around either negative infinity or positive infinity. Or even in set notation, we use like less than or greater than. We can't use the actual equal sign because it's not a value, it's a concept. If it's positive infinity, it's that our values are getting large and arbitrarily large and positive. And if it's negative infinity, the values are arbitrarily large and negative. All right, so now that you understand that, you may have learned how to find a vertical asymptote, but it would be maybe a surprise to you that the definition of a vertical asymptote deals with limits. You should be copying this down. The line x equals a is a vertical asymptote of the function, of the graph of a function, y equals f of x, if either the limit of f of x as x approaches a from the right equals positive or negative infinity, or the limit of f of x as x approaches a from the left is positive or negative infinity. So what that means is that, and this is not a graph or even a sketch, but like let's say we have a coordinate plane and there is a vertical asymptote. Okay, by definition, it exists there because maybe on one side it's going down towards negative infinity. Okay, it's quite possible that over here there's a point on the asymptote and it goes up like that. Okay, depending on how the function is defined, but it's still considered a vertical asymptote because one of the one-sided limits, okay, is positive, or in this case, negative infinity. Okay, so that's why it's a little confusing to students when you see some functions to have horizontal or vertical asymptotes, but somehow the graph is touching it. And this is why, because it's actually defined by limits, okay, which obviously is a calculus topic, and you can't really discuss calculus when you're first learning hyperbolas back in Algebra 2. All right. As a side note, and hopefully you were copying this part down too, is that the limits can both be positive infinity, they could both be negative infinity, one could be positive, one could be negative. And just stressing again that there's an or. It doesn't have to be that both are true. A lot of times that is the case. You have a vertical asymptote and it looks something like this. And it could be more than one. Okay, so giving you that heads up. Okay, so besides Algebra 2 being introduced to hyperbolas and asymptotes, you have also gone over it in pre-calculus and have found vertical asymptotes. So this is kind of a review of what to do. Set the denominator equals 0 and solve. Okay, you're probably solving for x because x equals is a vertical line. So just remember, you're describing a line, it should be x equals. A would be a number. But step 2 is very important. Substitute the value back into the function. If the result is 0 over 0, it's not a vertical asymptote. If the result is a non-zero number over 0, then there is a vertical asymptote of the function. Okay, that's what you want, and that kind of just checks that this is true. If this is not true, then this is not a vertical asymptote. So really super important, okay? Now, an example where it doesn't have vertical asymptote, and you should know this because we went over this, and this is something you should know because you memorized its limit. Y equals the sine of x over x. Now, this is not a sketch or graph, but kind of a sad drawing here. Okay, but it does have a hole in the graph when x is 0. So if you plugged in 0 into your function, you're going to find you get 0 over 0. So this actually indicates a hole, whereas this indicates there's a vertical asymptote. So super important. Okay, and let's get to some examples. Okay, so for this example, you want to find the limit of 2x plus 1 over x minus 3 as x approaches 3, and the corresponding one-sided limits. So let's first identify, we have a rational function, so there could be a vertical asymptote. So that's step 1. Step 2, we're going to plug it back in. So you know what? We get 7 over 0. There's a non-zero number over 0. So that means that is indeed a vertical asymptote. So I'm going to draw the graph here. Where there's a vertical asymptote. Okay, at x equals 3. Okay, and we've got our x-axis, our y-axis, our scale, so it's a nice graph. Okay, that we're forming. There's another thing that I'm going to put in. You should know how to find the horizontal asymptotes. If not, that's okay. There's one at y equals 2. We go over that soon. So now, points. If we plug in 4, we should get 9. And if we plug in 5, we get 5.5. I'm doing the best I can with my graph here. And if we plug in 6, we get 4 1/3, so just bear with me. Let me put the function in. And let's go to some other x values. So when x is 2, we plug that in and we get -5. And if we plug in 1, we get -1/2, 1.5. I don't know, it's in there. And if we plug in 0, then we're getting 1 over -1/3. So really close to the x-axis. Okay, I'm doing my best here. And you're going to notice that as x approaches 3, our one-sided limits are different. So we can't have an answer here. This does not exist. We can't even use infinity or negative infinity, because here we go. From the left-hand side, it's following along this curve, and the values keep on going down. They're getting arbitrarily large and negative. So this is negative infinity. From the right-hand side, they keep on going up. They're getting arbitrarily large and positive. This is positive infinity. Okay, and that's what's going to happen when you have vertical asymptotes. You can also check with a table. Okay, so you can see in the table here that the limit value, if it's the limit of our function as x approaches 3 from the left. So you're going to notice that the y values aren't really consistent. It goes from a -2,000 to -3,500, and then almost -7,000 It's not slowly increasing, or in this case, slowly decreasing. So you would maybe think it's negative 10,000 as the next value, or maybe even negative 100,000. It keeps on getting arbitrarily large and negative. So that's where we're getting the negative infinity. And from the right-hand side, you can see a reminder, you can highlight the y values, that it is big. It has a 2,335 and a third as its y value. And then it goes to 3,502 and so on. It keeps on getting larger and arbitrarily large and positive. So that side was positive infinity. Okay? Okay, so last one, I'm going to find the limits of 6 over x squared as x approaches 0, and the corresponding one-sided limits to that. And the first thing we're going to do is, just like we did before, substitute in 0 into our function, and you know what? We get a non-zero number over 0. So this is indeed a vertical asymptote at x equals 0. That's by plugging in our x value. So let's start drawing the graph. Okay, so as we draw our graph, bear with me. 3, 6, 1, 2, 3. I'm doing a graph again. Again, you can do a sketch, which still has labeling for our points. Wherever you plot a point, and you should be plotting points, you have to label what numbers they are. So here we go. The first point I'm going to put in is not a point. I'm going to put in my vertical asymptote at x equals 0. And there's actually a horizontal asymptote on y equals 0. Again, we'll review that in case you don't know how to find that. So here we go. 1, 6 is a point, okay, and 2, 1.5 is a point, so I'm already close to that horizontal asymptote. And if I just connect these two, I now made it a sketch. If I plotted more points, then it would be more of a graph. If you plugged in 3, you would get about 2/3. So since it's hard for me to draw on this, especially graphs, I'm just going to leave out that point and we'll do a sketch. So next, if I plug in -1, I'm going to also get 6. And if I plug in 2, I'm going to also get 1.5. So you know what? This side is similar to the other side. Okay, they're reflections of each other on the line x equals 0. So let's get to our one-sided limits. So the limit from the left-hand side, it goes up and it goes towards positive infinity. And from the right-hand side, same thing's happening. So you know what? We can say that they don't exist, but we're indicating our answers with infinity when possible. So in part A, instead of just leaving it as does not exist like the previous problem, since both of these are the same and they're positive infinity, I can also say this answer is positive infinity. So a little bit different than the last one, and that's why I'm going over example 2. I want to show you the table for it. Hold on. Okay, so the values from the left increase and the values from the right increase. Just want to say, if you see E, usually that means 0, but if you highlight the Y value, it's actually not 0, but rather it keeps increasing. You see that one's 6 million. And so the previous one was actually 1,500,000. So it does definitely jump towards positive infinity from both sides. So hopefully you understand what we're doing and how to get our answers, and good luck.